in two main parts. The first part would be going through the general overview and then the structural analysis, different type of analysis that we are doing for the bridges. Talking about the time history analysis, different type of time history analysis that we need, or it's well known and it's being used for structural analysis, especially for bridges. Then talking about the displacement time history, the requirements for displacement time history, why we are doing that, and how we have to handle that. Then talking about the next part, we'll be talking about that if we are doing the displacement time history analysis, what are the considerations that we have to keep in mind and satisfy for running a correct analysis, because when it comes to the nonlinear type of time history analysis, you most probably need a strong software that can help you with the modeling and setting up all those nonlinearities and different type of forcing functions that you need. So we're going to go through those details and talking about the substructure and also the soil structure interaction option, and also how to generate the forcing functions for such analysis. To start with, I'm going to just give you a quick overview about the structural analysis. So when we're talking about the structural analysis or bridge analysis, we are talking about mainly four groups, static and dynamic, and each of them could be linear or nonlinear. We're talking about the static linear analysis would be like a very simple type of loading, let's say like a self-weight loading that you have on your structure, or all the gravity loads. You're going to see what's the response of the structure to that, and that will be a basic static linear. That's pretty common for most of the bridges, and that satisfies the needs for some of the bridges in different regions. But that might not be the end of the story. For several bridges, we need to go into the dynamic analysis to see how the structure or the bridge going to respond to a dynamic or seismic event. So for that purpose, we have two main analysis, dynamic analysis type, response spectrum and time history, which the response spectrum is a linear dynamic analysis, meaning the linear means here that material remains linear, and then the soil structure interaction, we're going to consider them all as the linear. This type of response spectrum analysis is satisfying for most of the bridges, which even they are located in the highly seismic zones. Depends on the size of the bridge, on the number of spans that you have, and then the depth of the site. All those are different parameters, but most of the DOTs or organizations just require you to do the response spectrum to find out the demand or dynamic demands on the structure. On the other hand, we have the time history analysis, which the time history analysis we consider as a nonlinear type of analysis, because we are considering the nonlinearity of the material. For example, when you have your pier or you have your pile or even your the girders, not only we consider their we take care of those linear or elastic behavior of the structure, we are also going to see the nonlinearity on this structure, or seeing like a more capacity of the bridge when it goes to the plastic zone. So in this way, we are just utilizing more of the capacity of the software. So we're going to talk about those details later in this presentation. So these two types that I mentioned about the dynamic analysis, response spectrum and time history, those are run the structure to find out the demand on the structure. So by demand, I mean what will be the total displacements, like deformations, all the internal forces, what will be the response of a structure to that type of loading. On the other hand, we have the static nonlinear analysis or pushover analysis, where we are running this type of analysis to find out the capacity of the structure. So I have the bridge, I want to know what's the capacity of my bridge. So one way to find out that that capacity is to just push the structure until it fails. And then failure, we consider it by the, defining the plastic hinges, which later on we're going to see them in the detail. So here I just want to show you the general overview of the structural analysis and what we are doing for the building and bridges, but today we're going to just focus on the bridges. Now let's talk about, just focus on the time history analysis and see what type of time history analysis we can run. So here I just show you three simple types, which is mostly used for the structures. The first one would be, for example, the machinery vibration, or if you want to consider the, for example, vibration of a train on your bridge. So that would be kind of like, this type of, for example, sinusoidal type of forces you can apply on the structure, or it could be different examples. We are not going to discuss about this today. I'm going to just show you like different types. Another one would be, for example, applying the normalized acceleration of the ground based on the specific earthquake. For example, the San Francisco earthquake. So you're going to see what happens, what this function, forcing function, going to do to my structure. So it depends on where you are constructing the bridge. So you may use different type of, normalized acceleration functions. And also we can define that forcing function could be a displacement. So it's going to be the displacement of the ground during a seismic event. So you're going to see what's happening, and then we're going to discuss about this, that how we can generate such a displacement time history. All right. So as we discussed today, we're going to talk about the displacement time history analysis of the long bridges. Let's see what's the displacement time history and where do we need to use those guys. Okay, so displacement time history is the history of the ground displacement during an earthquake event. So that's pretty simple definition. So it meaning that when you have earthquake in center location, what will be the displacement of the different part of the ground responding to that force. And then we can use that function to run the apply the force on the, for example, the new bridge that I'm going to generate right now. When do we need to use this type of displacement time history analysis? So displacement time history analysis, you're normally not going to use them for the regular bridges or like a conventional or highway bridges, but it's mostly used when you have a long bridge, or something similar to this bridge that you see here, when we have like a deep piles. So when you have a deep pile, what happens is that the different layers of this, the pile or are covered by different type of soil. For example, in the top layers we have the clay, then we have the sand, then we have the rock. So definitely the behavior or the soil structure interaction would be different in different layers. So in such a situation, we need to run the displacement time history analysis. And not only the soil structure interaction would be different, but also when the earthquakes come to the experiencing different layers, those waves definitely gonna generate different type of forcing. So we're gonna talk about them, that how those are generated. But in this slide, you're gonna see that what's the need of this displacement time history. So this is one technique that we're normally using it for long spans, or when you have like a deep piles where the different layers of soil exist in that location. So let's see what happens during an earthquake. So when an earthquake happens, so different ground motion you're going to see. So we see that in a different location of the ground, let's say this is, let's say 4,000 feet, and then so definitely you're going to see different ground motion experiencing there, and that ground motion will be transferred to the location of the piles or the your columns, depends how the foundation is set up, and then those guys experiencing different forcing functions. All right, and then the next part would be that those guys, those forces, gonna shake the structure, and after the structure is shaken, now what happens is that the structure give us a response. So that response, it means the displacement, the formation of different parts. It could be internal forces like a moment, shear, axial forces. So those are all considered as a response of the structure based on the the earthquake force that we applied on them. And once again, different part of the ground or different part of the bridge experiencing different forces. Okay. So let's just summarize it and showing you the steps for the seismic design of the long span bridge. So for the seismic design, as I said, we need two parts. One will be the checking the capacity of the structure. One is to see what's the demand on the structure. Once again, displacement time history is run to find the demand on the structure. So what we do, what an engineer does, is that we apply the ground motion to the foundation, which causes the shaking the structure. And as we discussed, different displacement time history functions would be applied to the different location of the ground. Once again, this might be a different location of the different piles, or it could be also a different location in the depth of the pile also. So for example, in the this slide, we may have different forcing function here and different forcing function right in the middle of this pile. Depends how deep is that and how many layers of the soil you have there. Then we have to consider the nonlinear material and boundary conditions. So the material itself, like the columns or the pile, they showing the nonlinear behavior, as well as the soil structure interaction has the nonlinear behavior as well. So the way that you're pushing the soil in the dynamic event, how that's going to respond. So this will be the details that are going to come up. The next step would be getting the response of the structure, like a bending moment, shear forces, displacement, reactions. So all those that the engineer need to get to do the design. Based on those responses, as we discussed, a bridge engineer need to just do the design the different elements of the structure, like a superstructure, like a substructure, foundations, like bearings. So now we're gonna discuss about different part of the bridge or different components, how we have to take care of those guys. Once again, when it comes to the displacement time history, and you have a large structure, and you're seeing the nonlinearity in those elements, and nonlinearity in soil and structure, so there's it become kind of complicated analysis. And doing the hand calculation, I can say it's impossible, or it's going to be impossible in a short time. So you need to spend a very long time to do it with a hand calculation or a simplified method. But so you definitely need to have a sophisticated software, something like one of our software, MIDASoft, which you can easily handle this part for you. You can completely model the structure. You can consider the nonlinearity in the, model the soil springs, nonlinear soil springs. You can model the nonlinear elements of the material, and also run apply the different forcing function on different part of the structure. So that's kind of, the kind of requirement to run different this displacement time history analysis. Now in this slide you see that we have different forcing functions, and we have the unique forcing function at different location of the foundations. We're going to define the nonlinearity for material and define the nonlinearity for soil structure interaction. All right. So what consideration we need for the displacement time history for a long bridge? I'll put it in 3 parts, talking about the substructure, talking about the foundation itself, and finally we're going to talk about the forcing function. So these 3 would be the main important part of this presentation. For the substructure, I'm going to talk about how to define the nonlinear property or nonlinear behavior of the bearings, which is a part of a bridge, and normally we are using them, especially when we have these seismic events. Then we're going to talk about the column itself, and then formation of the plastic hinges in those, and then we're going to talk about using the plastic capacity of the columns, and then how to run the analysis, and how to generate or how to find out those plastic behavior or plastic hinges. For the foundation, we're going to talk about the methods that are available to find out the modeling the abutment or modeling the soil behind the abutment, because that's pretty important. And if you just ignore those, for example, soil springs, you're going to come up with a completely different response of the structure, which might be not what you are looking for. All right. And also, after that abutment, we're going to talk about how to model the piles, because when we have the piles are surrounded by the soil, we have to simulate the soil springs, and then there are different methods. When you have like a large structure, what you have to do. When you have like a smaller structure, what you have to do, and then different methods for generating those options. So we're going to talk about the direct method and also the substructure method. And finally, we're talking about the forcing function, because what happens in an event, in an earthquake, is that mostly the accelerations and the velocities are recorded by the machines, now by accelegrams. Now, if you want to run the displacement time history, what's the method to get those displacement functions? All right, so we're going to talk about two general methods and explaining that how those guys gonna help you to generate such a forcing function. All right, so let's start with the substructure. Today I'm not going to talk about the superstructure itself. But once again, if you're using any software like MIDASoft, you can define nonlinearity to any part of the superstructure. But for these seismic forces, mostly the substructure and foundation would be more important to define those nonlinearity for them. And then most of the time, the plastic hinges happening in the column itself, and then there are a possibility to have like a collapse in the structure, in the event, in the superstructure, but that's a different story. We're not going to talk about them today. All right, so one part is the bearings. So bearings, we are normally using them to connect the superstructure to substructure. All right, so this connection has two components. If you look at these bearings, we have the one vertical, when the superstructure is sitting on the your columns. So that's a vertical transferring the forces. Another one would be transversely, which is in this direction, Y and Z direction. So what happens there, when you have the earthquake, these bearings gonna show you the nonlinear behavior. As you can see, for example, similar to such a curve, which you can see that it's not going linearly, increasing the displacement. By increasing the forces, the displacement is not increasing linearly, and as you can see, is nonlinear. This is very good and very useful for us. We're going to talk about the advantage of using these bearings, but now we're going to just talk about the behavior for now. Well, this bearing shows a kind of linear in the regular static forces. For example, this first part, you see that this is a kind of linear part. So that linear part, we're going to see them in when you have the moving load analysis, when you are doing the, for example, regular gravity forces. Those would be the linear part. And these bearings are pretty important because, you're doing this type of analysis, like time history analysis, both for the new structures, when you are constructing a new structure, so you need to design, you have to ensure that that bridge is good enough to handle all type of forces that it might experience. And also, we're doing this time history analysis for existing bridges. So there are some existing bridges which may not have enough, capacity to be able to handle certain type of, earthquake, because they've been constructed like 40 years ago, 50 years ago, which, maybe there wasn't enough information for the seismic design. Now we're gonna rehabilitate those, and therefore, you run the displacement time history, or in general time history analysis. Now, I said that these bearings are important because personally I saw there are many cases then for the old bridges, or existing bridges, that they weren't able to, they didn't have enough capacity for the seismic events, and then there were like plans for the rehabilitating those. If you want to do the rehabilitation, if you want to increase the sections or doing any type of those, that's one part, because it's going to be so expensive. But I saw so many cases that just placing the bearings for the different part of the structure, like in abutments or on top of the pier, and those can be pretty economical, and then it can save the structure a lot, because when we see these, like this nonlinear behavior of these bearings, so what happens is that the energy will be dissipated while you have the experience. So therefore, the forces which are coming from the ground, this will not be transferred. Most of them will be dissipated, and then just a small part of that will be transferred to the superstructure. So we're going to have, the structure going to function perfectly even during the seismic events. So this is pretty important, and it could be used for the existing bridges as well as for the new bridges. Another part of this substructure would be the column. So I have like one image here which shows you how the column may behave under a seismic event. So definitely we're going to have the deformation. Normally, probably we don't consider the plastic deformation of the structures, or the material like a concrete or even steel. We don't consider those for the regular analysis. But when it comes to the seismic analysis, if you want to just consider this, the elastic behavior of the structure, sometimes you may need to have a very large, section to respond to that much of force, because the dynamic force, you can just consider it as a static force, which has like a magnifying factors as well on top of those. So the more, if you increase the size of this sections, so what happens is that you're going to have more self-weight there, you're going to have more masses there, and then that mass is going to absorb more energy, and it's going to kind of like contradicting each other. So you're just increasing the size, and then the force will be more, and it goes on and on. Definitely it's not going to be economical. So what we're going to do, we're going to consider, or we're going to use the plastic deformation of the structures for the seismic design as well. Now, how to understand what is the plastic deformation and when we are gone to the plastic zone. One of the methods that we are handling this part is to define the plastic hinges. So if you have such a column or a pier, if you push this structure, the connection, just assume that there's a fixed connection in the top and bottom. The top is kind of fixed. It's maybe not 100% fixed, but we can assume it as a fixed. There are two parts right here and right here in the top that there is a possibility of the formation of the plastic hinges. Okay, so that means that the structure is going to fail through those points. All right, so what we can do, we can find out the plastic hinge or plastic hinge property, which is a function of the material that I use, for example, the concrete that you use there, and then the rebars that you use there. So combination of those guys would be leading to finding out those plastic hinge behavior. And that's pretty important, because the failure of this structure probably would be considered by when the first plastic hinges forms there. So it's going to be the ultimate, or going to be the failure of that structure. All right. You can find out the, for example, if you are using software MIDASoft, you can simply define, generate those moment curvature, which we're going to talk about that. That's the next slide, and then assign it to different part of the column. So it depends how the connection of the column might be. So you may have different parts for the plastic form, but more than 90% of the time we're just applying the plastic hinges to the bottom of the column, because that's the highly possibility for the formation of the plastics from the, just simple structural analysis. All right, but how to find out those things? I mentioned that that plastic hinges or plastic behavior of the column is based on the type of material that we use. For example, assume that this is your column. All right, it's a circular column. I have some reinforcement inside that, and I use certain grade of the concrete. Let's say grade 5,000. All right. So based on those, we can generate we can find out what is the plastic behavior of that column. All right. One well-known method is to find out the moment curvature. So the moment curvature, for finding out the moment curvature of a certain section, what we need to define nonlinear material first. So how to define those nonlinear material? In this column, like a reinforced concrete column, I have my concrete, which has two parts actually. You see the pink part right here, which is the confined concrete. This is confined because we had the confinement spiral or ties around them. So it's a kind of concrete inside that has, showing us the better behavior or better response. So you can see from this diagram right here, which is the Mander model. This is one of the model, the concrete model that most of the, seismic codes in US are recommending. For example, AASHTO SDC is recommending that one, and Caltrans also recommending that one. Other states also using this Mander model. So this is pretty sophisticated model, and as you can see, there are two models in the Mander model. One is for the unconfined. As you can see, this is the force versus stress versus strain, or you can say that force versus displacement, but stress strain would be better. And now here we see that this one, the unconfined, doesn't have that much of good performance, while if you have a confined concrete, the same material with the same grade, with the same compressive strength of concrete, you see that it's gonna show you better performance, and it's gonna absorb more energy, and it can have like better, nicer performance. This is why we are separating the concrete to the confined. Inside the, the core concrete will be confined, and then the cover concrete will be unconfined. So this is pretty well-known method. I'm just explaining them for people who are new to this method. And then for the rebar, most of the codes like AASHTO and Caltrans and all other states that have the seismic design criteria, they allow us to use the bilinear curve for the steel, like using the elastic, perfectly plastic. So we don't consider this strain hardening part. But if you are using software like MIDASoft, there you are able to, not only you can define the bilinear curves like a elastic, perfectly plastic curves, but also you can model the, using this park model, which giving you the realistic behavior of the steel. And as you can see, it's using the strain hardening part, and it's gonna go all the way to the ultimate capacity of the steel. So this is pretty helpful. Anyway, so you need to define these first. These are the requirements for being able to generate the moment curvature. And then what you do, just run the, using any software. You can also use the hand calculation, but it takes time probably. And you can generate such a behavior. So it's going to be the behavior of this column under which we are on the y-axis we have the moment, and under the x-axis we have the curvature. So curvature will be easily calculated based on the shape of the deformation of the column technically. But what you probably need to use at the end of the day for defining that plastic hinges right here, to define this plastic hinge, would be just considering this bilinear curve, the blue line that you see here, which we call it idealized curve. So this idealized curve would be good enough, and then software understands, whatever software that you're going to use, it's going to understand that until this point of the moment, which is on the structure, on the column, it's going to go linearly upward, and then from that point, it's going to be a plateau, or kind of is yielded, you can say that. Okay. So there are way more options that we can talk about, the moment curvature, how to generate those, how to improve them, and blah blah. So, but that's the limitation for the time. We can't talk about those guys more than this. Now we're gonna go to the next part, will be the foundation. In this foundation, as we discussed earlier, we're gonna talk about the modeling the abutment or the soil springs behind the abutment, as well as the foundation itself. I mean the piles and pile groups. That's pretty important to model the abutment itself, as you can see is modeled right here. And more importantly, it's important to model the soil behind the abutment, because that's gonna give us more realistic response of the structure. Just consider that if you simulate or model the entire structure with the simplified method, for example, simplified method, I mean, in the abutment, you just ignore the abutment and just apply the simply support there, or you're like a fixed support there. So definitely you are coming up with some sort of the assumption, and that's not leading to a economic design, because you are just doing the analysis on some other type of a structure. So if you want to see like real behavior and then make it like a more realistic, that's the way that we're going to do that. We're going to model the entire part of the structure, and also we can simulate the soil behind that. And then for simulating the soil behind the abutment, there are a couple of methods. For example, the initial one would be just to get the results from the in situ test, like a geotechnical engineers, they can do the test for you and then tell you that this is the springs for the structural engineer, and then structural engineer can apply the springs in a different direction that is provided at different point of the abutment. But there are some simplified methods also. For example, you see this method based on the different parameter of the soil. You can simply calculate these springs. As you can see, this behavior, this curve is giving us the non-linear behavior of the soil behind it, because we have to kind of assume, not assume, we have to understand that the soil has like a non-linear behavior when it's interacting with the structure, and depends on the forces, it doesn't deform linearly. Or there's a simpler method. This is kind of older method. It's a classic method being used with a lot of engineers. But there are also simplified method, more practical. This method is generated by, developed by Caltrans, I believe. And then they have like just this simple equation. With this simple equation, you have two parameters, C and D, which need to be calculated by these two simple equations. And all these values that you see here, K, Y, F, R, these are all the soil parameters. Easily you can generate those, easily you can find them, and then, just fill up this equation, find the C and D value, then you're going to, based on that, you're going to come up with such a curve. This is so easy. And for example, Y maximum for the sandy soil going to be the 0.05 H, which H will be the depth of the abutment, or the height of the abutment, or the depth of the soil that you have. And there are different options for the cohesive soil. So these will be kind of constant, depends on the height, and then you're going to calculate this K 50 based on the slope of this line. Easily you can just go ahead and get your curve defined. All right, and then if you are using the software like MIDASoft, you can simply define such a curve inside the Midas, and then you see that that the springs behind the abutment have exactly showing you exactly the same deformation as you're applying the forces. Even these equations are become simpler to become like more practical, and then less complexity, just very simple and straightforward. So this is the equation. I got it from the Caltrans, and I believe we have the same thing in the Ashta as well. And then based on for the sand and clay, as you can see, we have the constant values, and then we can simply use these to calculate the abutment soils, springs. Now let's talk about the foundation. So this part might be more interesting because selecting a different method can affect the time of analysis and can affect the total response of the structure more than what the abutment does. Just assume that you have such a long bridge, and then you have many pier caps, and under each one you have a group of piles. So all these are the pile cap, and then the piles underneath those. So the question is, how should I model this one? There are two main methods. One is the direct method that you saw it here, which means I'm modeling entire structure, superstructure, substructure, and foundation all together. And the second method is substructure method, which means I'm not modeling all these piles because there is some advantages on there. I'm going to talk about them. And then replacing entire the pile group, like entire this one, with only one spring, which carries, that spring should carry the behavior of entire the pile group. Okay, by that one I mean, for example, if you have one keeps force applying on the structure and has, for example, this much, or let's say 1 inch of this deformation on the this part of the substructure, you have to have exactly the same. You have to have exactly the same matrix on the 6x6 matrices to show you the exactly the same amount of displacement. So it's a kind of like challenging to calculate those 6x6 matrices, which is a good representation or is a good substitute for the entire pile group. There are different methods to calculate those as well. But what is the advantages of using this one, and what's the disadvantage of using the other one? So each of them have their own advantages and disadvantages. And in a different situation, you may consider to using any of those. That completely depends on the need of the project, whatever you want to accomplish, and what you want to design. That's completely based on the project, and then definitely the time that you need to consider for the drawing the analysis. For example, let's talk about the direct method. So the direct method gonna give you a very accurate result, because what we're doing here, we are modeling entire the superstructure, substructure, and foundations, and all the piles all together. So we're gonna see the interaction between the superstructure and substructure, and then the foundation. So that's pretty, giving us a very good result in this way. And then the response of the structure would be very accurate and very close to the real response of the structure in the field. Okay, but there are also a couple of things that we should do. For example, assume that you have 50 of these micropiles here, and then you have to simulate the and each pile, let's say, have 20 feet, 30 feet, or 50 feet deep, and then those are experiencing different layers of the soil. So definitely you need to apply different springs at each point. So because they don't have the same spring response. So in the next slide I'm going to show you that how we utilizing the PY curves to calculate those things. But I'll just explain this to tell you that how heavy gonna be the model if you use such a model. Okay, so probably the analysis that you're gonna run on this one, it takes a long time, but it's gonna give you correct results. On the other hand, if you don't have enough time to run the a full analysis, full model, run the analysis on entire the model, so you better use the substructure method, which means you just ignoring these, not ignoring, you just deleting entire the piles and then replace them with one matrix, one springs, which has the mass, damping, and stiffness matrices as 6x6, which is, those 6 are 6 degrees of freedom, which you can model. Okay, let's talk about the direct method. I'm going to just explain that more. Here I have a zooming the one part of the my pilot system, and as you can see, I can simulate the springs and the damping of the soil at that location. That's what I modeled here, and then applying the different stiffnesses to different location of the pile. the question is how you're gonna find out those springs in a different depth of the pile. Answer is you can get those results from the geotechnical people. So geotechnical engineer just run the pushover like a pushing the structure. I can call the pushover also there, and then they getting some PY curves in the lateral directions. All right, and then based on those, based on the different depth of the soil, as you can see here, pile has different deformation, and definitely based on the different layer of the ground, and then the force that they're experiencing, you may have different stiffness. For example, here in this curve, P versus Y, which is the load versus displacement, I can find out this slope of this, linear slope of this soil as a spring, as like when I'm connecting this point to that point. And as you can see, as I'm going deeper, it's gonna be steeper, and then probably have like a larger steepness. The same story goes on for the vertical or the frictional stiffness, which we have to do the TZ curve. So the TZ curve, in this case, we are pushing the, applying the force laterally to the structure to find out the PY curve. But for the TZ curve, we are applying the forces in the vertical direction, and then again finding the response of the structure. As you can see here, we got these TZ curves for the different depths, and as you can see, this one also getting steeper as we're going deeper in the pipe. All right. One more thing. So far we talked about the simulating the springs, okay? But that's very important. You have to consider that that springs is just representing the nonlinear behavior of the soil and the structure, okay? But depends on the depth of the pile and then the location of the piles, those nodes or that part of the pile may also experience different forcing function. As you can see here, I have this forcing function applies on this location, I have this forcing function applies on different location, and different one at different location. So that's pretty important to be more accurate and then consider different forcing function if you have like a pretty long bridge where the site is changing, the soil layers are changing, or if you have like a deep pile. Okay. There are simple equations for curves and equations and all those simplified methods for calculating the that stiffness or PY curves. Here I have one simple example. This is a risk model for the sand. So you can see that how the curves for different depths. These are the different depths along the depth of pile, and how to calculate these values based on the total width of the pile, and then how to use these curves. Here I have some simple typical K values for these sands, so you can just simply use any of those. But to be more accurate, we definitely need to define those options. Now, after you calculated this one, how to apply these on the structure? I have some example which you can, there are some constitutive models which widely used by the engineers. I'm just explain a couple of those. The first one is the kinematic hardening. So what you see here is kind of showing you, the behavior of the soil by this model. Here I have on the y-axis I have a p-value, which is a force, and the x-axis I have a displacement. So you can see that this hysteresis loop going up here, then loading, it's going to be nonlinear, has a different slope, and then when you have an unloading, you're going to see the plastic deformation in this area, and then again changes the slope, plastic deformation goes on. So you can see that by increasing the loads, this loop is going on, and then you see also the plastic deformation of the the soil. So that's pretty important. Kinematic hardening model is mostly used for non-gapping behavior. So just assume that this way. If you have like a pile, okay, and the pile is surrounded by the soil, which means if you push the pile in any direction, so you're gonna see the soil around it gonna resist that deformation. So we're gonna see that that the springs or that nonlinear behavior is already there for both directions. even you push it from the left to right or right to left. But if you have like one wall, just a retaining walls, in one side we have only the soil, right? So we're gonna see that the springs behind the wall only from one side. So that's the difference between like a gapping and non-gapping behavior. All right. So when you say that a non-gapping behavior, I'm talking about the compression and tension, which would be, one example would be the pile, where it's surrounded by the soil from the all directions. Well, we have the Takeda model, which normally used for the modeling a non-gapping, gapping behavior, or talking about just the compression only. Just an example of that retaining wall. Just assume that if you push the structure, push the wall, so you're gonna see that it's soil gonna resist it. But if you're gonna pull it or just pull the wall, there's no resistance, but the strength of the wall itself. Right? You can see the different behavior also here. Just following these curves, you're gonna see that this is a trilinear curve. One line here, then you're gonna have the first yielding at this point going up, then they're going to be the second yielding, and then we're going to have a the unloading and on. There are different methods also, like a pivot model. So they have also different parameters. You're going to define them, and the software going to follow those curves. But to be more accurate, we are providing a more accurate type of inputs for the users in MIDASoft, where you can just apply the force versus displacement, which you are getting from the PY curve directly here into MIDAS, and you can just copy paste the data from the Excel to here to simulate the exact behavior of the spring. That could be only the compression or only tension, or it could be goes both directions. So you're going to see when it goes like this way, you're going to see the plastic deformation of the soil. When you have an unloading, it's going to come back with the first slope of the, that curve. All right. So this is pretty impressive and useful when you want to model a more accurate type of nonlinearity. But for simple structures, you can use any of these functions, and they're going to give us you pretty good result. All these methods, all these constitutive models are also available in MIDASoft. All right. So let's talk about the second method, which is the substructure method. So in the substructure method, we say that we have to look for one substitution for the pile system. So I'm gonna delete the pile system and then place only one spring. That spring should have the 6x6 matrices of the mass, damping, and stiffness. Okay, those are the three main parameters in the dynamic analysis, right? So if you check the classic equation of the dynamic equation, we're gonna see mass versus the acceleration, and then we're going to see the damping versus the velocity, and we're going to see the displacement versus the forces. Okay. So how to do that? How to find out these parameters? So all these members of the matrix for the stiffness and the mass would be simply calculated. For the mass, you can simply calculate them, that how much of the mass gonna be contributing for different direction. As you can see here, we have the K11, which is for the dx, dy, dz, and then rotational degrees of freedom. So that's pretty simple. There are methods of this. There are like some simplified method. I know that a couple of DOTs, like I believe the Caltrans is providing this one. Washington DOT, I saw some paper on them that they're providing some solution how to calculate those things. So you can search for them. And after calculating these matrices like a stiffness and the mass, then you can simply use these use such an equation, which is the Rayleigh method, and then in this method you need to find out the alpha and beta value, and then based on those you can simply calculate add these matrices with those coefficients, and it's gonna give us the technically the damping matrices. All right. So I covered the first two parts, which was talking about the nonlinearity part. Now let's talk a little bit about the forcing functions. So if you remember in the beginning of the presentation, we talked about the way that the earthquake is recorded by those accelerometers. So how what we're getting with the acceleration and probably velocity, and most of the time we are just normalizing the acceleration, and that's the normalized acceleration is widely used for the running the time history analysis. But now, assume that we have such a site. As you can see, there are different layers of the soil, and then the rock, and then different parts. And each of those definitely based on the property of those soil layers. The earthquake which is coming here will be definitely, those waves will be different when they are reaching to the ground or reaching where the, my pile gonna be located. All right. So definitely each pile gonna experience different forcing. Now, how to generate those, displacement time histories? When you have the acceleration time history, so the first method would be using it's going to be the direct integration. Because based on the classic methods, we take the first derivative of the, first integration of the acceleration going to give us the velocity. And then if you take another, integral from this one, it's going to give us the displacement. So definitely there are some, additional numbers gonna be here, so we can just go through all those and then find out those variables. But this is just simply I'm just showing you what equation is gonna be. So taking the direct integration and then come up with such a displacement forcing function. So you see that with the same time history, with the same time, if this is my acceleration, this is gonna be the response of the displacement of the ground at that certain location. Another method is to use the Fourier series. So we can simply have the acceleration from the accelerogram, and then using the reverse Fourier transformed, and then calculate the displacement time history. And then simply we can use this for your analysis. I have one example for you showing you that if we have such a long bridge, how to simulate the here you see the nonlinear behavior of the bearing. So definitely the displacement are exaggerated. Just hopefully you can see that the formations. It might be a little slow through the internet, but that'll be nice if you can see these options. So here we see the nonlinear behavior of the the bearings, as well as right here you see that the nonlinear behavior of the columns as well. So we can simply follow, if you use MIDASoft, I took this video from the MIDASoft. If you use MIDASoft, we can see exactly when you're applying the plastic hinges to the column, you can exactly follow the columns, and you see that in a different level of the forcing, if any of those columns or any of those plastic hinges are formed, and then you have the failure of the structure. So that's pretty useful in this way. All right, that's it about the presentation today. Now, if you guys have any questions, I'll be happy to answer to those questions. They asked if where they can find out the copy of the software, the presentation. We're going to have it on our website, and then we're going to share it with everyone after the presentation. They asked if we can assume a point of the fixity for the pile with the displacement of the 0 inches, and then ignore the springs. I didn't quite understand the question, but let me just show you what we have here. For example, here you see there is a change in the when we have like a pile and then we are pushing it in the laterally. So we see that there is a change in the, for example, here is where the curvature is changing, and we can call it like a point of inflection. So probably we have the 0 moment at this location. All right. So probably you can just fix the structure from that point, or you can find out where with the displacement 0, and then you can fix it at that point and ignore the whatever is below that. But that's not, I don't recommend that, because we have the active behavior of the soil and also passive forces, because when you're simulating this pile, or if you have like a retaining wall or whatever embedded structure in the soil, we're going to see the, when you're pushing it even from left to right, we're going to see some forces from here, and then we're going to see also some forces right here in the left side. So that's pretty important. You have to consider those to come up with, for example, even if you want to follow the simplified methods of Bishop and all those also require to have those forces. I don't recommend it to ignore that, but again, it completely depends on the case, and sometimes we may, if we ignore that, we are not seeing that much of changes in the response of the structure. So yeah, if it's the case, definitely just ignore that, because it's definitely going to reduce the size of analysis and definitely going to save your time and save your money. They're asking about the soil spring. I mean, considering the damping in the soil springs. You can consider the damping in the soil springs, yes. The damping will be considered as a linear damping. So, yeah, we can consider that one. But what's the value for that depends again on the soil. But I believe like a 5% or less would be considered here. They asked what happens to the software if the shaking the structure causes the column to fail. So that depends what type of analysis you are running. If you are running a let's say pushover analysis, so we can just ask the software to having, for example, the displacement control or force control, or you can just tell the software if the the hinges is reaching the second yield, just stop them and terminate the analysis. You can do that, or if you want to just consider that one, you can just, ignore that one. You can just go to the end of the analysis. But there's a way to terminate the analysis, and the software stops at the point of failure. So you can definitely understand what is the point of failure in MIDASoft. Yes, they asked. We didn't show how to apply these cases, and I mean they define this nonlinearity in MIDAS civil. That's completely correct because this presentation was the general information about the displacement time history. We're gonna have the training sessions. If you guys are interested, we're gonna provide the more training sessions for the showing you exactly how to apply this, how to simulate this nonlinearity for soil springs, for plastic hinges, how to generate the moment curvature, how to apply the displacement time history, how to define different forcing functions. All of them will be provided in the next session. But today it was just about the general presentation and general information about this type of analysis. Yes, they asked if the soil damping can be provided in the term of an attached dashpot. Yes, that's correct. In MIDAS civil, we have the springs, which is linear and nonlinear. We have dashpot. Dashpots are just linear. And then we have different type of base isolator, different type of bearings. Yeah, those are completely doable in MIDAS. You can define them.